Alright, so in this video we're going to look at the tangential and normal components of acceleration, as well as some formulas for curvature and torsion. So recall our standard notational setup. We'll say we have a curve C and a smooth curve with a smooth parameterization. If we take the derivative of this parameterization and take its length and integrate, we end up with the arc length function. The derivative of the arc length function, by the second part of the fundamental theorem of calculus, is the same thing as the length of r prime. Keep in mind, if we re-parameterize with respect to arc length, then this formula becomes r prime's length is ds, which is 1. We end up with a unit speed curve. Okay. And often it's helpful to assume that we're dealing with an arc length parameterization so that we have a unit speed curve, because it makes formulas so much simpler. But in practice, of course, this is almost always impossible to actually find the arc length parameterization, so it's mostly just a theoretical crutch. Next, recall the definitions. The unit tangent is the derivative of our parameterization normalized. And then the unit normal is the derivative of our unit tangent normalized. And then the binormal is a cross product of those two. And of course, t and b, they're all unit vectors. They're all perpendicular to each other. They're a right-handed system in the sense that t cross n is b, n cross b is t, and b cross t is n. Right? They work like I, j, k. Next, let's recall curvature. Curvature is the length of the derivative of the unit tangent with respect to arc length. The chain rule then gave us this other formula that's length of t prime over length of r prime. And as a quick example to keep in mind how to interpret curvature, recall that curvature for a circle is the reciprocal of the radius, meaning the bigger the circle, the less curvature it has. The smaller the circle, the more curved it is. And then lines have no curvature. Their curvature is 0. If we keep in mind the way that n is defined, then if you take the definition of n and you multiply and divide the denominator by r prime and reinterpret length of t prime over length of r prime as kappa, do a little bit of algebra, we end up with this nice relationship, that the derivative of the unit tangent is curvature times length of r prime times n. If you use an arc length parameterization, this becomes an even nicer formula. With respect to arc length, t prime equals kappa times n, because with respect to arc length, the length of r prime is 1, because we're dealing with a unit speed curve. All right, now let's seek to see what happens when we differentiate b. We'll come back to differentiating n maybe in a different video or at some later point, but the derivative of b is kind of interesting. So b prime, this would be t cross n prime. Well, by the product rule for the cross product, this is the derivative of the first guy, cross the second, plus the first, cross the derivative of the second, right? That's our product rule. But keep in mind that t and n, these guys, they're parallel, right? Because n is just t prime rescaled. So a cross product of two parallel things is 0. That goes away. So what we just discovered then is b prime is t cross n prime. So in particular, we just learned that b is perpendicular to t. Okay, b prime is perpendicular to t. Next, consider recall the important fact that if you have a constant length vector valued function like b is length 1, then we know that any constant length vector valued function is perpendicular to its derivative. So in particular, b prime is not just perpendicular to t, it's also perpendicular to b. Well, the only thing that could then be true then is that b prime must be parallel to n, right? Because we've exhausted the other two directions. So let's go ahead and make a definition. Okay, we now know that b prime is perpendicular to n, or parallel to n, so in the arc length parameterization, we're going to define b prime Well, we know it's some mystery thing times n. It's parallel to n. Let's call that negative tau of s. Okay, tau, this multiple that shows up, or off by minus sign anyway, tau is torsion, right? Oops, let me try that again. So torsion is a companion to curvature. Okay. We can also come up with a formula, a more kind of practical, in some sense, formula for torsion that doesn't refer to the arc length parameterization as follows. Recall that we have the chain rule that the derivative of the binormal with respect to s would be the same thing as dB dt times dt ds. And this, of course, is the same thing as dB dt divided by ds dt. Oops, let me scroll up a little bit. But we know that the derivative of s with respect to t, that's the derivative, that by our formula up here is the same thing as r prime. So we end up with that b prime of t is divided by length of r prime is the same thing as dp ds. So putting that together, we end up with b prime of t equals negative torsion times r prime times n. Right. And so there's a formula for torsion that doesn't refer, I'm off the edge of the screen, that does not refer to the arc length parameterization. So we'll see if I can get this drawn in here too close to the edge. All right, and that's analogous to what we had before for the derivative of t. So we also have this for the derivative of b. Okay, so that's the definition of torsion. Torsion says how the binormal is changing. And if you remember, the binormal is perpendicular to the osculating plane, and so torsion gives a measurement of how the normal of the normal vector for the osculating plane is changing. And so in some sense it's a measurement of how not planar our curve is. In fact, let's draw our attention to this fact again, that that the binormal is constant. That means that our osculating plane isn't changing. This is the same thing as saying our curve C is a planar curve. But now we know that this is the same thing as saying torsion is 0. So no torsion, because that would mean that the derivative here is 0. No torsion is the same thing as saying we have a constant binormal, and this is all the same thing as saying our curve is a planar curve. Okay, now let's come back to our other issue. Here we wanted to talk about the tangential normal components of acceleration. So keep in mind, acceleration is the second derivative of r, so this is ddt of r prime. Okay, but wait a minute, we know that r prime is the same thing as the length of r prime times t, right? That's the decomposition of r into its magnitude and its direction, because the unit tangent is just r prime normalized. Or if you want to see that more algebraically, t is r prime over the length of r prime. The length of r primes there would cancel, and we'd be left with just r prime. Okay, well, let's take the derivative of, before doing that, recall that the r prime is the same thing as the derivative of our arc length function. Remember, that came from our important formula right up here. Okay, and so using the product rule, we have s double prime t plus s prime t prime, right? That's the product rule. Okay, and then we can rewrite this, keeping in mind that t prime right? This is, we already have a formula for this in terms of the unit normal. Namely, we have right here that t prime is kappa times the length of r prime. Also keeping in mind that s prime is the same thing as the length of r prime. So we can rewrite, and we get that this is the same thing as saying s double prime t plus, okay, and then replacing this other stuff, we have kappa times r prime squared, right? Because we got one r length of r prime from our formula over here, and the other length of r prime comes from how t prime is related to n right over there. All right. So we end up with this nice formula. R prime double prime is s double prime t plus kappa length of r prime squared n. And notice what we just found out. This is kind of interesting, that the acceleration, right, is equal to something times t plus something times n. There's no b. So I'll put that over here. 0 times b, right? There's no binormal component, and there's no binormal component in acceleration. You always accelerate into the plane spanned by t and n. In other words, you always accelerate into the osculating plane. Okay, we're going to give a name to this decomposition. We're going to call that AT and this AN. Those are the tangential and normal components of acceleration. So if you like, the binormal component of acceleration is always 0. Okay? And later we'll want to have maybe a better formula for AT and AN. All right, moving ahead, let's consider now, I'm going to go ahead and delete all of this, or clear this page. Okay, fresh space to work with. Let's find a better formula. Oops. Find a better formula for curvature and torsion. Okay. So first of all, let's consider r prime cross r double prime. Its length. Okay. It seems kind of a random thing to consider, but you'll see. We have r prime. It's the same thing as s prime times t, right? Because s prime is nothing more than the length of r prime, and so this is just decomposing r prime into its magnitude and direction. Next, r double prime is s. This is the acceleration, so we can rewrite it as its tangential and normal components. Okay, keeping in mind that s prime is the same thing as the length of r prime. We use that formula a lot. Okay, and so if we look at this, notice that we have a cross product t and t. If we distribute this, well, t. If we take two parallel vectors, right? If A is parallel to B, we know that their cross product is 0. So this doesn't contribute anything, right? Next, what we have is this is the same thing as the length of, and let's pull out common factors. We have a s prime and an s prime squared, so that's an s prime cubed. We have a kappa, there's another scalar valued function, and what we're left with is t cross n. Oh, but wait, we know what t cross n is. That t cross n is just b. So we're taking the length of, well, let's pull some things out of the length, right? S prime is positive, so it cubed is positive. We don't need an absolute value there. Kappa, the way we've defined it, curvature is non-negative, so we don't need an absolute value there. We're just left with the length of b, but it's a unit vector, it's 1. So let's rewrite s prime as the length of r prime. So we just ended up with the following. The length of the cross product of r prime with r double prime is the length of r prime cubed times kappa, and so we get this rather handy formula that the curvature can be computed. Let me be a little less sloppy there. The curvature can be computed by computing the cross product of the first two derivatives and dividing by the length of r prime cubed. Let me show you a quick example using this. If you take, let's say, take something called the twisted cubic, t squared, and t cubed. All right. If we were to compute curvature using our previous definition, we'd have to find the unit tangent and differentiate that, and that's really kind of a pain. It gets ugly. I encourage you go check that out. Try to find the unit tangent for the twisted cubic. All right. Now, finding the first and second derivative here, though, that's no problem. R prime, let's see, its length. It's not that it's super pretty, but it's easy to write down. So we have 3t squared is 9t to the fourth, 2t squared is 4t squared, and 1 squared is 1. The cross product of the first two derivatives, again, we imagine I, j, and k up there. We have our mnemonic device. I probably need more space than that. The I component, we have 2t times 6t, that's 12t squared, minus 2 times 3t squared, that's minus 6t. The j component, we have 1 times 6t, and then minus 3 times t, 0 times t squared, so that's minus 0, but it's the j component, the whole thing needs to be negated, so we end up with a minus 6t. And then the k component, we end up with 2, 1 times 2, minus 0 times 2t is just 2. Okay, so long story short, what do we have? We have 6t squared minus 6t and 2, which we can, of course, factor a 2 out of that. We have 3t squared minus 3t and 1. So if we find the length of the cross product here, that's just 2 times the square root of 9t to the fourth plus 9t squared plus 1. And putting that all together, we now have that kappa for the twisted cubic is the square root of 9t to the fourth plus 9t squared plus 1 divided by 9t to the fourth plus 4t squared plus 1 raised to the 3/2 power, because it was the square root, but then it's cubed. Okay. So it's relatively easy to compute curvature, find a formula for it, if we use this formula. Let's go ahead and mention that we can also use this formula for curvature to find a nicer formula for tangential and normal components. Okay, so keep in mind that the normal component for acceleration is kappa times the length of r prime squared. Well, we now know that kappa is the length of the cross product of the first two derivatives divided by r prime cubed. So just 2 copies of r prime cancel off, and we're left with this rather nice clean formula for the normal component of acceleration. Okay. Next, just to kind of sketch this out, the normal component of acceleration then, remember the way the length of the length of a cross product is length sine theta, where theta is the angle between r and r prime and r double prime. This cancels, and so you're left with r double prime, length of r double prime sine theta. Okay. Well, if you want, as a companion to that, the tangential component of acceleration then must be length of r double prime cosine theta. And if you consider the way that t and n are oriented in the plane, you can treat t as if it's an I vector and n as a j vector, then it makes perfectly good sense why we would have, you have t and n here. Why, if n's component is r double prime sine theta, then why t's component is going to be r double prime cosine theta. Anyway, long story short, if you can multiply this by r prime over itself, and we recognize the formula for the dot product, right? And so we end up with the tangential component is r prime dotted with r double prime over the length of r prime. And so there's our tangential component of acceleration. Isn't that nice and clean? So the tangential component is r prime dot r double prime over the length of r prime, whereas the normal component is the length of the cross product of r prime r cross r double prime over length of r prime. Finally, I want to mention torsion also has a nice kind of formula in terms of just the derivatives of r. Torsion, if you think about it, involves a derivative of b involving n, and so kind of it shouldn't be surprising. It actually involves a third derivative, and so here's our formula. It's r prime cross r double prime dotted with r triple prime all over the length of the cross product of r prime and r double prime quantity squared, length squared. And so the top of that is a triple scalar product, right? It's a 3 by 3. The top you could compute by a 3 by 3 determinant, where you create a matrix whose first row comes from r prime, second from r double prime, third from r triple prime. And then the bottom is, again, just the length of the cross product of the first two derivatives. That gives us a nice clean formula for torsion. If you wonder where that comes, I'll add a supplementary video deriving that. And so, thank you.